So the next chapter which we are going to cover is the second chapter of conic section, that is the ellipse. Getting started with the first problem, we are given that if normal at the end of a lattice rectum of x square by a square plus y square by b square is equal to 1 passes through an end of the minor axis, then we need to prove the relation e power 4 plus e square minus 1 is equal to 0, where e is the eccentricity of the ellipse, and also we need to find the ratio of the lengths of the major and minor axis. So in all these kind of problems, let us first make the figure. If this is the ellipse x square by a square plus y square by b square is equal to 0, this is a comma 0, minus a comma 0, 0 comma b, and 0 comma minus b. Let this be a point at which the tangent is made, and this is the ends of the lattice rectum. Let this be ae comma b square by a. You should always remember the coordinates of focus, the endpoints of the major and minor axis, the endpoints of lattice rectum, and the directrix of the ellipse. If this point is ae comma b square by a and we make a normal on this, then it will definitely pass through 0 comma minus b. So let us proceed with the problem. Differentiating the equation, we get 2x by a square plus 2y by b square is equal to 0 into dy by dx, is equal to 0. This dy by dx represents the tangent at any point on the ellipse. So the slope of tangent is equal to minus b square x1 upon a square y1, if x1 comma y1 is the point at which the tangent has been made. So the slope of normal will be equal to a square y1 upon b square x1, which is the negative reciprocal of slope of tangent. On putting x1 comma y1 to be equal to ae comma b square by a, we get slope of normal to be equal to a square into b square by a divided by b square into ae. B square cancel, a square cancel, we get the slope of normal to be equal to 1 by e. So writing the equation of normal at the ends of the lattice rectum, we get y minus b square by a is equal to 1 by e times x minus ae. And since this normal passes through the end 0 comma minus b of the minor axis, putting x equals 0 and y equals minus b, we get minus b square by a is equal to 1 by e times minus ae. This minus gets cancelled, ee gets cancelled. So we get, on solving this, we get a square minus b square is equal to ab. And for an ellipse, we know that b square by a square is equal to 1 minus e square, where e square is the eccentricity of the ellipse. Hence, dividing this whole equation by a square, we get 1 minus b square by a square is equal to b by a, and we know that b by a is equal to under root of 1 minus e square. So putting the values over here, we get 1 minus b square by a square is 1 minus e square is equal to b by a, which is under root of 1 minus e square. So this becomes e square is equal to under root of 1 minus e square. Squaring both the sides, we get e power 4 is equal to 1 minus e square, or e power 4 plus e square minus 1 is equal to 0. Hence our first relation has been proved. We wanted to prove that e power 4 plus e square minus 1 is equal to 0, where e is the eccentricity of the ellipse. Now we want to find the ratio of the major and minor axis. We know that the length of major axis is 2a and the length of minor axis is 2b. So the desired ratio is a upon b, and since we had a square minus b square is equal to ab, and this is a square e square is equal to ab, hence we get b by a is equal to e square. So our desired ratio is 1 upon e square. Now from this biquadratic equation, we have e power 4 plus e square minus 1 equals to 0. On finding the root, we get e square is equal to root 5 minus 1 upon 2. So our ratio will be equal to 2 upon root 5 minus 1, and the denominator can be rationalized to get the relation as root 5 plus 1 by 2. Hence the first part, in which we needed to prove e power 4 plus e square minus 1 is equal to 0, gave the root e square as root 5 minus 1 upon 2, which gave the answer for the second part for the ratio of major and minor axis to be equal to root 5 plus 1 upon 2, and this is our final answer.